let's just jump right in. Scientists aren't just your standard researchers in lab coats. They're really more like planetary detectives. In this explainer, we are going to decode the completely dynamic history of the Earth's surface. We're going to unpack exactly how we read the hidden scars, the shapes, and the massive shifts of our planet. We'll actually start our journey by looking down at Earth from space. When Apollo 14 astronaut Edgar Mitchell looked out his window, he described it so perfectly. He said, "My view of our planet was a glimpse of divinity." And that's a pretty common shared sense of awe among those who've actually seen our planet from orbit. It's this brilliant, dynamic puzzle just suspended right there in the blackness of space. And from those orbiting spacecraft, we can clearly see the macro changes happening on that puzzle. We see the constantly shifting cloud formations, the sprawling orange-red deserts of Africa that just stand in this stark contrast to the deep blue oceans. And we can see the really intricate, deeply indented coastal fjords in places like Greenland, where these massive glaciers literally carve up the landscape. So here's the crucial point. While we can easily see the big picture from space, how do scientists actually go about measuring the invisible, excruciatingly slow forces that are shaping the ground right beneath our feet? How do we track something that feels entirely, completely solid to us, but is actually in a constant state of flux? Section 1. The Science of Geomorphology, from Description to Deduction. Okay, so in the mid-20th century, this field underwent an absolutely massive revolution. Basically, scientists threw out the old inductive approach, just looking at landforms and kind of guessing their historical cycles. Instead, modern geomorphology shifted to a deductive, heavily quantitative approach. They started aggressively measuring the real-time, contemporary processes that are actively creating the landscape around us. And to pull this off, they rely on a seriously unconventional toolbox. They aren't just looking at regular rocks anymore. No, they're analyzing the weathering rates of marble tombstones to clock chemical breakdown. They measure misfit river valleys to calculate ancient water volumes. They track ancient wind directions using fossilized sand dunes. They even look at tufa mounds to find past groundwater and analyze displaced archaeological sites, like literally fractured sections of the Great Wall of China, to see exactly how much the Earth has shifted beneath human history. How cool is that? Moving on to Section 2, Measuring the Ground Beneath Us, Decoding Neotectonic Processes. Now, you might remember when Alfred Wegener first hypothesized his famous theory of continental drift, it was just that, a theory. People thought it was a bit crazy. But today, neotectonics allows us to actively track these massive shifting plates and prove those ideas right. And the method they use is just wild. Scientists literally bounce space lasers off retroreflectors that were left on the moon by Apollo astronauts. By perfectly timing the light's return trip, they can track the exact motion of the Pacific plate relative to North America. And the sheer precision of this method, it is absolutely staggering. This lunar laser ranging technique tracks tectonic movement with an accuracy of just 1 centimeter a year. 1 centimeter. We are literally using the moon as a fixed yardstick to watch the ground slide right beneath our feet. But it's not all space lasers. Scientists also deploy a vast array of high-tech sensors right down on the fault lines. We're talking about using satellite altimetry to monitor changes in the Earth's geoidal shape, very long baseline interferometry, or VLBI, and these highly sensitive wire-type creep meters and electronic tilt meters dropped deep down into boreholes. All of these tools constantly gauge the slow, hidden buckling and creeping of the Earth's crust, giving us a real-time pulse of our planet's tectonic activity. Which brings us to Section 3, Reading Past Climates, the Microscopic Time Machine. Okay, so we know how to measure the crust today, but how do we look back millions of years to decode ancient weather? Well, don't let the math here intimidate you, because this formula is essentially a microscopic time machine. By calculating the ratio of oxygen 18 to oxygen 16, scientists unlock a permanent microscopic thermometer that's locked inside ancient materials. Think about it like this. By applying this math to fossilized marine organisms, like those tiny foraminifera extracted from deep-sea sediments, scientists can actually reconstruct the exact temperature of ocean water from the Pleistocene era. That is well over 1 million years ago. And they don't stop there. They also use isotopic carbon from ancient soils and animal diets to track major environmental shifts. And they look at amino acid ratios in fossilized mollusks to determine past site temperatures and ages. It's really chemical detective work at its absolute finest. And alongside all that chemistry, they also analyze tiny biological clues.
Researchers sift through sediments to find specific climatic indicator species. By identifying ancient beetle communities or establishing complex numerical transfer functions from fossilized pollen, they can trace exactly how regional climates, environments, and temperatures shifted over millennia. I mean, if you find a specific cold weather beetle in a specific layer of dirt, you know exactly what the weather was like when that dirt was up on the surface.
All right, Section 4, Decoding Sea Level Changes, Tracing Ancient Shores. So, the mass transfer of water and ice over millions of years leaves these massive structural scars all across our landscapes. When mapped out on a height distance diagram, like this one here from southeast Scotland, we can clearly trace ancient beaches that are now stranded high above today's sea level. They're literally just sitting on dry land, kilometers away from the current coast. And these stranded shorelines are actually the result of a fascinating geological process called isostatic rebound. Imagine firmly pressing your hand down into a memory foam mattress and then taking it away. The foam slowly springs back up, right? Well, that is exactly what the Earth's crust does. During the ice ages, massive glacial ice sheets crushed the land downwards. When that ice finally melted, the land began to slowly rise back up, lifting those ancient beaches dozens of meters into the air over thousands of years. To track these oceanic shifts over time, researchers drilled deep down into coastal bogs and tidal flats. By analyzing sequences, like this really detailed one from Down Holland Moss, they look at alternating layers of marine clay, freshwater peat, diatoms, and pollen to create a super precise timeline. For example, if you find terrestrial peat that's covered by marine clay, that proves a rising sea flooded the land. If it's the other way around, the ocean retreated. They even use pumice to date these ancient beaches, which is just brilliant. Pumice is this highly distinctive floating volcanic rock. When a volcano erupts, pumice floats right across the oceans and eventually washes up on shorelines across the globe. Because each piece of pumice can be tied chemically to a specific dated volcanic eruption, scientists use it as a perfect floating clock to sync up ancient beach formations worldwide. Bringing us to our final part, Section 5, The Future of Our Past, Continuing the Investigation. So, by tracking those microscopic isotopes, literally bouncing lasers off the moon to prove Alfred Wegener right, and reading fossilized beaches, we are continuously decoding the Earth's incredible autobiography. Which really leaves us with a final provocative thought to ponder. As the Earth continues its constant dynamic motion, what geological signatures are we leaving behind right now? When the planetary detectives of the distant future read the crust of the Earth, what exactly will our layer in the rock tell them about us? Thanks so much for exploring this explainer with me today.